Hello everyone, today we're going to be doing the Mathcounts 2000 National Sprint Round questions 21 through 25. The first question is, moves are only allowed one segment to the right or one segment up. How many paths from A to B are possible? So let's see, we can only move right or up. So we want to find the most efficient paths. How many paths from A to B are possible? So let's see here, we have this path, and then we have this path, and we have this path, and then we also have this path, this path. So we have a lot of paths. So how do we approach this problem? Well, first of all, we can find how many ways to get into each point, and then we can add it up. So let's see, how many ways, so let me zoom it up here. How many ways can we get to this point over here? Well, there's only one way, by just going up. So there's only one way of getting there. What about this point? Well, same for that one. There's only one way, going right. And what about this point? There's two ways. We can go up and then right, or right and then up. So there's two ways there. So it's two. So it's two here. And then what about here? There's only one way, and then here there's three ways. And then we could kind of see that there's a pattern. The number of ways to get to any block is just the sum of the block on the left plus the block on the bottom. So we can see here, since this is 1 and this is 1, this is 2. Since this is 2 and this is 1, this is 3. So we can use that pattern, and then we can keep going. So first of all, we can just label all of these 1 because there's only one way. We can't go left or down. And then since this is 3, this should be 4. And there's only one way, which is go up from there. And then 4 and then 1, that's 5. 5 and then 1, that's 6. 6 and then 1, 7. 8 and then 9. And 4 plus 5, that's 9. 9 plus 6, that's 15. 15 plus 7, that's 22. Only one way, 22 here. 22 plus 8 is 30. 30 plus 9 is 39. And then 22 plus 30 is 52. So our answer is just 52 plus 39, which is just 91. So there are 91 paths to reach from A to B using this method. Okay, moving on to the next question. It says compute 100 squared minus 99 squared plus 98 squared minus 97 squared plus all the way down to minus 1 squared. So what do we do here? There's first a minus and then a plus and then a minus and a plus. We can see here that there's a lot of difference of squares. We have 100 squared minus 99 squared, and we also have a 98 squared minus 97 squared. And then if we have a difference of squares, that's equal to the sum of these two numbers times the difference of the two numbers. Since if we multiply that, that's a squared, that's ab, and then we get a minus ab and then a minus b squared, and these two cancel out, and we get that. So let's try the same for 100 squared minus 99 squared. So we have 100 plus 99 times 100 minus 99. So that's just 199 times 1, which is 199. And then we can keep going. 98 plus 97 times 98 minus 97. That's just 197 minus 2, which is 195. 195 times 1, which is 195. And then we can observe a pattern from now on. It's just technically 100 plus 99, and then the next two is just 98 plus 97. So technically, all this is doing is just the sum of all numbers from 1 to 100. So just 1 plus 3 all the way to 99 plus 100. And there's a pretty easy way to solve for this. So the first number plus the last number we can see is 101. And what if we add the second number to the second to last number? We also get 101. So why would we be getting the same number? Well, as we increase one, the other side decreases one, so it evens out, and then we get the same number. So we can see it's just 101 times how many pairs are there? There's 50 pairs. So our answer should be 50-50. So the answer to this question is just 50-50. Moving on to the next question. What is the sum of the three numbers less than 1,000 that has exactly 5 positive integer divisors? So what does it mean to have 5 positive integer divisors? That means you have exactly 5 integer divisors, no more, no less. And then what is a divisor? It's any number that can be divided into a number. And there's a quick formula to solve for the number of divisors. After we put it into prime factorization, which is just like a to a certain power x, and then times b to another certain power, and then these are all primes, we can get the powers of the prime. We have to add one and then multiply it into each other, and then we get how many factors there are. So why would you have to add one to each side? Because we don't need to use the prime number. We can have it as 1. Let's take 12 for example. So how many factors do 12 have? Well, let's put it into prime factorization form first. 2 to the second power times 3. So we can see here just 2 plus 1 times 1 plus 1, which is equal to 3 times 2, which is 6. And then we can confirm by seeing 1, 2, 3, 4, and then 6, and then 12. So there are 6 factors indeed. So why would we add a 1? Well, as we can see here, 1, 3, and 1 and 3 don't need any 2's in there. So it's just 2 to the 0th power. And let's see, if the number of factors is 5, then that means that when they multiply by each other, it should be 5. But 5 is prime, which means we can't get any two prime numbers that multiply into each other that get a 5. Which means the only possible way is if this number has a prime number to the 4th power, because we can see the factors is just 5. So we're trying to find how many numbers have the 4th power, but we also have to be careful. For example, like 1 to the 4th power is just equal to 1, but as we can clearly see, there's only 1 power here, so have to be cautious. And then the next number is 2 to the 4th power. That's 64. Actually, no. That's 16. And then we have 1, 2, 4, and then 8, 16. And we do indeed get 5 factors in here. So 2 to the 4th power works. I don't know why I said 64. So 16 works. And then let's see, 3 to the 4th power, that's equal to 81. And 81 is just 1, 3, 27. There's a 9 as well. 9, 27, and 81. So that one also has 5. So 81 is also an option. And then let's see, 4 to the 4th power. 4 also has factors of 2 and 2. So technically, it's not 4 to the 4th power. It's 2 to the 2nd power to the 4th power. So we have to make sure that we're able to find that out. So 256 doesn't work. And then we move on to 5. 5 is 625, and then let's confirm it real quick. 1, 5, and then 25. 125, and a 625. So that also works. The three numbers, and we already have 3. So we can just add it up. 16 plus 18 plus 625. 16 plus 81 is 97 plus 625. 725 minus 3, so 722. So the answer should be 722. The next problem is Ellen has 5 different jobs to be done. She assigns all 5 jobs to her 4 kids. Each kid will have at least 1 job. How many ways can Ellen assign these jobs? So, first of all, we know that there are 5 jobs to be assigned for 4 kids. So the first kid, and each kid has to have at least 1 job. So the first kid can have 5 different jobs. They can take the first one, second one, third one, fourth one, or fifth one. And then the second one will just take the other one. The fourth, so he has 4 options, and then 3, and then 2. So now each kid has a job. So the other kid, we can just randomly assign one of the kids to do. So times 4. So if we multiply that out, which is 5 times 4 times 3 times 2 times 4, we get 480. But if you assign the for example, if you assign the last kid one of the job, and then you assign the last kid the last job again, that's the same as assigning the last kid the first job first, and then the second one, and the second one and the first one. So there's an overlap. So we actually need to divide this by 2. So that's a 240. So think about it. If let's say we assign the first person job number 1, and we assign the second child job number 2, and then number 3, and then the last child we assign number 4, and then for the number 5th job we give it to the last child as well. That's essentially the same as saying I give the last child number 5, and then for the number 4th job I give it to them again. So that's the same. So we multiplied it twice, so we have to divide it again. So we get 240. So that's our answer. Okay, we're ending the video with a pretty fun one. What is the value of the following expression? Root 6 plus root 6 plus root 6 plus root 6. All the way down infinitely many times. So let's see. How do we approach this thing? There's just an infinite amount, and then if we see like root 6 plus root 6, and then if we put it in like the calculator, and then we try to calculate, it's like about 2.9. And then what if we add like another root 6? So add a root 6 plus a 6, and then we take the square root, and then we add another 6, and then we take the square root. We get like 2.98. And we're not allowed to use calculators in here, but we can see that it's approaching 3, but we don't know if it goes over 3. So we're not sure, but there's a pretty cheeky way to solve this. So we have an infinite array of 6's, and 6 plus root 6 plus root 6. Let's call this x. So we're trying to find what x is. And what happens if we square x? Then if we square x, then this one will be cancelled out. So we're left with equal to 6 plus root 6 plus root 6 plus root 6. And then we can see here that this is just x, because it's an infinite array. So we can substitute that into x. So we get x squared equals 6 plus x. And then rearrange it. X squared minus x minus 6 is equal to 0. So we get a simple quadratic equation from this complex expression. And then we can just factor it. X plus x minus 3. X minus 3 times x plus 2 is equal to 0. So either the following expression is equal to 3 or it's equal to negative 2. And it doesn't make sense that the result is a negative number, so we can cross that out, and we get the answer is 3. And then also we can kind of verify from what we just did. It kind of starts approaching it starts approaching 3, so we get like about 2.9 and then about 2.98, so it's getting closer and closer to 3. So but on the test we can't use a calculator, so this way would be the way to solve it. So yeah, that's it. Questions 21 through 25.